Hello students, welcome to Engineering Mechanics Statics. This is the second video that I'm making here. In today's video we're going to go over sections 2.1 to 2.3 in the course text. And this chapter is titled Force Vectors. In this chapter, the objectives are to show you how to add forces and resolve them into components using the Parallelogram Law, as well as the derivative law called the triangle rule. Another objective is to express force and position in Cartesian vector form and explain how to determine the vector's magnitude and direction. And the last objective is to introduce the dot product in order to determine the angle between two vectors or the projection of one vector onto another. And that last one will be covered in the next video. So let's go ahead and start this chapter. So section 2.1 is scalars and vectors. So you can't really describe a force vector without first starting with a description of what a vector is and also what is a scalar. A scalar is a quantity that has either a positive or a negative value to it, and only specifies the magnitude of a quantity, the magnitude of something. An example of a scalar is things like mass, or length, time, or temperature, things that can be described as individual quantities. Now, what is a vector? A vector is a quantity that has both a magnitude and a direction. Now, as you can see in the drawing here, the magnitude is typically denoted as the length, or the length of the vector, and the direction is usually denoted as an angle between some reference axes. So you define some reference axes. Let's call this axis x, and the angle that the vector makes in relation to that axis x is described as the direction. In addition, there is something called sense, and the sense is in what sense or what direction, sense of direction, is the vector applied, and that sense is usually denoted by an arrowhead at the end of the vector. So examples of vectors are things such as force, which can be applied in a particular direction along a particular axis or at an angle to a certain axis, velocity, acceleration, or position. The position of an object in space can be described as a vector. It's at a certain distance in a particular direction away from myself or from you. Vectors in the book are denoted as bold, uppercase, not uppercase, but are denoted as bold objects in the book. In my notes, however, because it's easier, I denote a vector by an arrow over the symbol. So in the case here, A with an arrow over the top. You'll see, depending on the book that you're studying with, or if you've got additional reference books, that different authors use different approaches. However, the fundamental equations are always going to be the same. So now that we've described what a scalar and a vector is, let's go into basic vector operations, which is 2.2. So a vector can be multiplied or divided by a scalar quantity. So say you have some vector A that has a magnitude, a direction, and a sense. Well, we could multiply that vector A by 2, by a scalar value of 2, and what it'll do is it will double the magnitude, but it doesn't change the direction or the sense. We can also multiply that vector A by -1, and what that does is it keeps the same magnitude, but it changes the sense of the vector and makes that sense opposite of what it previously was. We can also divide a vector. So say we divide a vector by half or multiply it by 0.5. And that's what we do in this last one here. We multiply by negative 0.5. And so we've changed the sense and we've changed the magnitude. So those are some of the basic things that we can, that's one of the most basic operations we can do to a vector. Now let's look at the problem or the issue of vector addition. So what happens when you have two vectors, a vector A and a vector B, and you want to add those vectors together? When we add them together, we can call that resulting vector a resultant vector. So in this case, R is equal to A plus B. So how do we actually do this? How do we do this, and how do we determine what the sense of direction of that resultant vector will be? So we have to find, the resultant vector is going to have a unique sense, a magnitude that is unique, and then an orientation relative to your axes of interest that's unique. So how do we add two separate vectors together and produce the appropriate resultant? One of the ways is to use the Parallelogram Law, and all vector quantities obey this law. So it's a very useful law. So let's look at the diagram here. And so in step 1, we have two vectors, a vector A and a vector B. They both have different magnitudes, they have different senses, and they have different angles or orientations. The first step of the Parallelogram Law is to make A and B, the starting point of those, coincident, so move them so that they're on top of each other, and then to actually create a enclosed parallelogram where two sides are equal at each point. So let's so we project A and we project B and create a parallelogram where two sides, each side is equal to the opposite side. Now notice when we create this parallelogram that we're using a head to tails approach, meaning this is the head. Well, this is the tail, so the ends of both vectors are coincident, but the head of the A vector meets at the tail of the B vector. So these, so that this head to tail is found at these locations. Now, once we created this parallelogram, we'll notice certain things. In particular, the angle that's between A and B is going to be the same in this opposite corner. And from that, we also find that the angle gamma in these two corners will be the same. And this is a useful property that we can exploit later on when we're trying to solve problems and determine the orientation of the resultant angle of the resultant vector, or the orientation of a vector that we are given, but we don't know the exact orientation. So now that we've created this parallelogram, we have the interior angles. The point where these additional vectors meet, we can describe as point P. And this point P is a very important point which we'll use in step 3. So in step 3, what we do is we create a dotted line that connects the coincident point of the original vector A and B with this new point P that we've created. And this line from the start point to point P is the length of our resultant vector. And so what we can do, so what we do in step 4 is we draw that length, and then we also put the arrow, we also draw the sense of the resultant vector. And that sense is going to be from the coincident point towards point P. So this allows us to determine the magnitude of the resultant graphically, but also determine the sense of that resultant graphically. And this is a fairly useful feature. Now let's look at the triangle rule. The triangle rule is a special case of the Parallelogram Law. It's a variation of it that kind of simplifies the application and determination of the resultant. Now, the triangle rule can be tricky because there are two different ways or two different approaches that you can use towards finding that resultant. So again, we're given some vector A and some vector B. They have their own different magnitudes, different senses, different orientations. How do we use the triangle rule? Well, again, we're going to use a head-to-tail approach. But in this case, instead of making the start point of vectors A and vectors B coincident, we use a head-to-tail approach. So in version 1, we start with vector A. So we draw vector A. And then we connect the head of vector A to the tail of vector B. And so we draw vector B. And we're moving this vector to the head of vector A. And we've drawn the vector B. Now what we do is the endpoint of vector B can be called point P. And so from the start point of A to the endpoint of B would be the magnitude of our resultant, and the resultant will have the same sense as the arrow, as the direction, or the direction, the general direction that vectors A and vectors B have. So you can see they're both pointing towards the right, so the resultant will be towards the right. It's a graphical approach, but it's fairly simple. Now let's do this same problem, but starting with vector B. So if we were to start with vector B, the tail to the head, and then we add vector A, head to tail approach, then the end, or the head of vector A, we can say at that point is point P, and from the start of B to the head of A, we have this line, which is the magnitude, and the sense of direction is going to be based on the enclosement of B and A. Now notice that the triangles that we form using the triangle rule each have unique angles, interior angles to them. There's not a similarity in those angles. But what we can do is later on we can use trigonometry in order to determine these angles A, B, and C. So now, what's a special case? A special case is, say we have two vectors that are collinear, meaning they have different magnitudes, but they're in the same direction. Well, in that case, the problem greatly simplifies the problem of adding them together. We can just say, put vector A head to tail with vector B, and at the end here is point P. So the magnitude of the resultant vector is going to be that length, and the sense is going to be the exact same as A and B. Fairly simple. Now what we can do is we can also do, now that we've completed the vector addition approach, or the issue of vector addition, we can also do vector subtraction. So that's when you're given two vectors and you want to subtract one from another and find the resultant of that. With that, it's the resultant vector is equal to the A vector minus the B vector, but it also can be described as the A vector plus a negative B vector. And so let's go ahead and do that. Let's use the parallelogram law and the triangle rule in order to try to subtract vectors. So let's look at the parallelogram law. We've got two vectors, a vector A and a vector B, and we want to subtract vector B. So what are we going to do? Well, the first thing we need to do is we need to change the sense of vector B, because it's a negative vector now. So we've changed the sense of vector B and make it have a sense that is opposite to its normal sense. So let me actually put this here, negative B, okay. With the parallelogram law, we have vector A and vector B. So we do vector A and vector negative B. We make their start points coincident, so they both start at the same point. And then we create a parallelogram that has the same magnitudes on each side. And of course, let's change this around here. Okay. Now that we've done that, we find the point where these mirrored vectors meet, and that's point P, and it has a certain length or magnitude to it. Now that we have that magnitude, we take the sense and we find our resultant vector R of this the subtracted of A minus vector B. Now let's go ahead and look at how do we do this same thing using the triangle rule. So again, we start with vector A and vector B. We subtract vector B, so we have a negative vector B. And then head to tail approach, we take A and from head to tail, vector A. And then from that, we find this point P. And from the start point of B to that point P is the magnitude of the resultant. And then the sense of the resultant is going to be an arrow that meets where the sense of A meets. And so we found our resultant vector. We can also do this same rule starting with vector A. So say we start with vector A, and then head to tails negative B, and we find here is point P, and from the start to point P is the magnitude of the resultant, and the sense of the resultant is going to be in the same direction as the arrowhead of, or at the same point where the arrowhead for negative B meets. So the parallelogram law and the triangle rule are both rules that you will use extensively in this class to solve issues of vectors and of force and position vectors, which are used all throughout statics problems. So in order to do well in this class, you must know both the parallelogram law and the triangle rule. You must know how to use both of those approaches. And you'll see in class examples why this is important. So now let's go ahead and move on to the next section here, which is 2.3, vector addition of forces. So finding a resultant force. So multiple force vectors may be added together to find the resultant force. So say you have a system of cables, and one cable is carrying a certain load, another cable is carrying a different load, different weights, which are forces, and they're connected to some tower. Each of these weights that have different angles, each of these weights or the loads in those cables have different angles. So, what is going to be the resultant force that goes through the main cable? That is a principal problem in statics. So, how do we, add up these force vectors? Well, we do it just like any traditional vector. So say we're given some force vector 1, 2, and 3, and we need to find the force resultant. Well, the force resultant, or the resultant force vector, is going to be equal to the sum of the various force vectors. So the sum of force vector 1, 2, and 3. And this can be an infinite number of forces. So as many forces as you have, you can solve for a resultant by summing them up. Another thing that you may be asked to do is find the components of a force. So say you're given a force that has some angle in some coordinate system. You can actually take that force and subdivide it into components that are directed along those coordinates. So a force vector may be decomposed into two components in order to study the push-pull effect in two specific directions. In the case of this example, I use directions U and V. Typically, you'd use direction X, Y, or Z and decompose a force into those types of coordinates. However, you can, using any coordinate system you choose, decompose a force. And this is a useful property that you'll probably use later on in the semester. Okay, so let's look at this diagram. So one here, we have a force vector in a coordinate system of U and V. where V is a little bit unusual. All right, now in figure 2 here, we start to decompose this force vector into its components. So what we can do is we can actually recreate the parallelogram rule, and we can actually draw out what the components of the force vector would be, and we get a force vector F. We get a component Fu, and we get a component Fv, and that's using the parallelogram rule. We can also use the triangle rule and take that force vector and decompose it using the triangle rule to get the same components Fu and Fv. Now notice that with the parallelogram rule, we get certain interior angles, the angular relationship between Fu and Fv. But in the case of the triangle rule, we get the angles of Fu relative to F and Fv relative to F. So these are, useful properties that we will use later on. So now let's go ahead and kind of look at the trigonometry. Let's look at the trigonometry of triangular geometry, really. So say we're given some triangle, which could be similar to this triangle representation up here. Say we're given some general triangle. It has lengths A, B, and C, which have some magnitude, and then it also has these interior angles A, B, and C. So the first thing we should all know is that the sum of these interior angles in the triangle, in any triangle, is going to be 180 degrees. So A plus B plus C is going to be 180 degrees. Now, there's two laws that we're going to use extensively in this class. There is a law of cosines and there is a law of sines. The law of cosines describes the relationship between the magnitudes of the sides of the triangle and one of the interior angles. The law of sines describes the relationship between the magnitudes and the angles of the entire triangle. The law of cosines is C, which is the larger length of the triangle, is equal to the square root of a squared plus b squared minus 2ab cosine of c, where c is the angle that is opposite the large side of the triangle. The law of sines is the magnitude a divided by sine of the angle a is equal to the magnitude of b divided by the sine of angle b, which is equal to the magnitude c divided by the sine of c. And these two relationships are quite useful relationships that you'll see repeated throughout the semester. Okay. So what are the steps to solving force vector problems? In general, there are two common problems that you'll face in this chapter. You're going to face the problem of given two vectors, or given two force vectors, find the resultant, and the resultant can be on a prescribed direction. So like a pulley. So the example of the cable system, where there's a cable tied to the roof, and there's two subcables that have forces at a certain angle. What is the force in that cable that's tied to the roof? You can also be asked to decompose a force vector. So say a force vector is in a certain direction, find the components of that force vector. Those are the two most common types of problems you'll find in your homework and in this section of the book. So what are the steps to solving these problems? The first step is to identify your knowns and your unknowns. So, what is the problem asking me to solve for? What does the problem give me? What are the initial things I'm given? And what do I need to solve for? That's the most important step. by putting that down, then you know where you're going to go. And as you write and you do your math, you know what direction your concluding equations need to go to. The second thing you need to do is you need to draw a free body diagram and label it. So take the force vectors, label them appropriately, put the information that you do know in there, identify ways to simplify the problem. So the same stuff from the previous video, where you must idealize the problem and simplify it in order to apply theory. The next thing to do is to use the parallelogram law. So take the force vector that you have or the components you have and create, using the parallelogram law, information about the problem. And the key things that you're going to be looking for are these interior angles. These interior angles are going to be quite useful to you. The next step is to use the triangle rule. With the triangle rule, you're going to get some different interior angles, the angles A and B, and those are quite useful angles as well. Notice that with the parallelogram law, the angle gamma that you have here is the same as angle C from the triangle rule. This is a very important thing to note, because this is how we link information from the parallelogram law and use it in the triangle rule. Once you've created these objects and you've found what angles you can find using geometry, then you use the trigonometry. So you use the law of cosines or the law of sines in order to solve these problems. And then you solve. And you apply those equations, you apply the known information you have, solve the equation, and put your answer. So that concludes the video for this section of the book and this section in the class. For what you should do after watching this video is please read the chapter section 2.1 to 2.3. Make sure that you read it thoroughly and complete your homework. Thank you for watching the video. My name is Dr. Stewart, and I'll see you next time.